July 18, 1944. The armored columns of 8 British corps thundered across the scarred earth southeast of Caen, their tracks churning through the pulverized remains of Norman villages that had, just hours before, been obliterated by the greatest aerial bombardment yet unleashed in support of a single ground operation. More than 2,000 heavy bombers had dropped nearly 7,000 tons of explosives on the German defensive positions, and now 1,200 tanks, the largest concentration of British armor ever assembled on a single battlefield, rolled forward in Operation Goodwood, their commanders standing in open hatches, scanning the smoke-shrouded horizon for the Tiger and Panther tanks they knew waited somewhere in the shattered landscape ahead. But the tankers of the 11th Armored Division, leading this massive assault, carried more than just their regulation ammunition and fuel. Welded, bolted, and sometimes simply hung with wire across their hull fronts and turret sides were dozens of spare track links. Heavy steel segments salvaged from destroyed tanks, scavenged from supply dumps, and in some cases pried from disabled German vehicles. To the staff officers and ordnance experts back at headquarters, this improvised modification looked absurd, a primitive and desperate measure that cluttered the vehicles, added dangerous weight to already overtaxed engines and transmissions, and violated every principle of proper armor design. The crews themselves called it their stupid trick, acknowledging with grim humor that they had no real proof it would save their lives. Yet, as the Shermans advanced into the killing ground where German anti-tank guns and Panzerfaust-wielding infantry waited in the rubble, every commander hoped that those dangling lengths of track might make the difference between survival and incineration. The problem confronting British tank crews in the summer of 1944 was not merely formidable. It was existential. The M4 Sherman medium tank, which formed the backbone of British armored divisions in Northwest Europe, had been designed in 1940 and 1941 as an infantry support vehicle, built around the reasonable assumption that it would face the German Panzer III and early Panzer IV models that had dominated the battlefields of France in 1940 and North Africa through 1942. The Sherman's armor protection reflected this original design philosophy. A frontal glacis plate of 63.5 mm thickness, sloped at 47 degrees to provide an effective thickness of approximately 93 mm, offered reasonable protection against the 50 mm and early 75 mm guns mounted on those earlier German tanks. The turret front carried between 76 mm on the standard Sherman to as much as 89 mm on later variants, while the hull sides, always a vulnerable area on any tank, were protected by only 38 mm of vertical armor plate. This protection had proven adequate, if not generous, in the North African campaign and the Italian fighting of 1943, where German armor appeared in limited numbers and American and British tank crews learned to use superior numbers, better reliability, and tactical skill to offset the qualitative advantages of the Tiger and Panther when those formidable machines appeared on the battlefield. Normandy changed everything. When British and Canadian forces came ashore on Gold, Juno, and Sword beaches on June 6, 1944, Allied intelligence had assured formation commanders that German heavy tanks would appear only in small numbers, that the Panther would be encountered rarely, and that the Tiger remained an exotic heavy tank produced in tiny quantities for special breakthrough operations. This intelligence was catastrophically wrong. The Germans had concentrated over 70% of their available armor in Normandy against the British sector. Recognizing that the Bocage countryside and the strategic importance of Caen made this the critical sector where the Allied advance must be stopped. Among these concentrated forces were significant numbers of Panthers, not the rare heavy tanks intelligence had predicted, but standard equipment for Panzer divisions, mounting a 75 mm gun with a 70 caliber barrel length that could penetrate 185 mm of armor at 100 meters and 149 mm at 1,000 meters. Against this weapon, the Sherman's frontal armor offered protection only at extreme ranges, and its side armor was utterly inadequate. The 88 mm gun of the Tiger could knock out a Sherman frontally from well over 2,000 meters, a range at which the Sherman's 75 mm gun could barely scratch the Tiger's frontal armor. Yet as devastating as the Panthers and Tigers proved in tank versus tank combat, an even more insidious threat emerged in the close-quarters fighting of the Norman hedgerows and shattered villages. German infantry, fighting from positions in the dense bocage that rendered long-range gunnery nearly impossible and reduced most tank engagements to point-blank encounters, wielded a new generation of man-portable anti-tank weapons that required neither training on complex equipment nor the physical strength to maneuver a heavy anti-tank gun into position. The Panzerschreck, a reusable rocket launcher firing an 88 mm shaped charge warhead, and especially the Panzerfaust, a disposable, single-shot weapon so simple that a teenager could learn to use it in minutes, transformed every German infantryman into a potential tank killer. The Panzerfaust 30, the first widely distributed version, could penetrate more than 140 millimeters of armor at its effective range of 30 meters, while the improved Panzerfaust 60, which began appearing in quantity by late summer 1944, extended this lethal range to 60 meters and could defeat up to 200 millimeters of steel plate. The Sherman's maximum armor thickness of 76 millimeters might as well have been tissue paper against such weapons. The psychological impact of these shape-charge weapons proved as devastating as their physical effects. Ken Tout, a gunner and later tank commander in the 1st Northamptonshire Yeomanry, wrote years after the war that the terror of the Panzerfaust exceeded even the fear of the Tiger's 88mm gun. You could see a Tiger, he explained in his memoir of the Normandy fighting. You could try to maneuver, to get a flank shot, to call in artillery or air support. But the Panzerfaust came from nowhere, from a hedgerow you'd already passed, from a rubble pile that looked like every other rubble pile, from a cellar window in a village you thought was cleared. One moment you're advancing, and the next there's a flash, a tremendous bang against the hull, and either you're still alive or your tank is on fire, and you have maybe 10 seconds to get out before the ammunition explodes. Tank crews developed a morbid vocabulary for the experience of being hit by shaped charges. A tank that caught fire was said to brew up, the black smoke pouring from hatches giving it the appearance of a kettle boiling over, and surviving crew members were darkly referred to as the brew crew. Statistics compiled by the British Army's operational research sections told the story in cold numbers. When a Sherman was penetrated by enemy fire, the probability of the tank catching fire approached 40%, and when fire broke out, crew casualties averaged 80%. The crews calculated their odds of surviving the campaign with brutal realism. Most figured they had perhaps a 1 in 3 chance of making it through without being hit, and if hit, only slightly better odds of getting out alive. In this environment of technological inferiority and statistical doom, the tank crews of 21st Army Group reached for any measure, no matter how apparently desperate or crude, that might shift the odds even fractionally in their favor. The practice of attaching spare track links to tank hulls began appearing in Normandy within days of the landings, spreading through informal channels as crews observed what their comrades were doing and copied any modification that seemed to offer even psychological comfort. No single officer or engineer designed this modification, no technical directive authorized it, and no formal testing validated its effectiveness before crews began implementing it on a massive scale. Track links were readily available. Destroyed tanks littered the battlefield, each one carrying spare track sections that could be salvaged, and supply dumps held additional stocks. The links were heavy, each one weighing between 20 and 30 pounds depending on the tank model from which it came, and because they were designed to mesh with drive sprockets and carry the weight of a 40-ton vehicle across all terrain, they were constructed of hardened steel significantly tougher than the mild steel or simple iron plate that might otherwise be scavenged for improvised armor. Perhaps most importantly, they required no sophisticated welding or fabrication skills to attach. A few brackets welded to the hull, some wire or rope lashings, or even simple hooks fashioned from scrap metal allowed crews to hang the links across their vehicle's most vulnerable areas. The innovation spread organically, driven by the crew's desperate need to do something, anything, to improve their chances of survival. Sergeant William Bill Close, commanding a Sherman Firefly in the 3rd Royal Tank Regiment, later recalled the process of up-armoring his tank in mid-July 1944, as his unit prepared for renewed operations after the brutal fighting around Cannes. We'd heard that the track links might help against the Panzerfaust, he wrote in his post-war account, and since Jerry was using those bloody things like confetti, we figured we'd give it a try. Some of the lads had already done it, and their tanks looked like they were wearing chainmail medieval knights going into battle. We spent a whole day collecting links from a knocked-out Panther. German track is thicker than ours, better quality steel we reckoned, and welding brackets onto the hull front. Must have added 24 links to the glacis and another dozen around the turret sides. The tank rode lower afterward, you could feel the extra weight, but we told ourselves that if it saved us from one Panzerfaust, it was worth hauling the extra ton or whatever it was. The theoretical basis for believing that track links might offer protection against shaped charges was sound, even if the crews themselves understood the physics only imperfectly. Shaped charge weapons, the revolutionary technology behind both the Panzerschreck and the Panzerfaust, functioned on principles entirely different from conventional armor-piercing shells. A traditional armor-piercing projectile relied on kinetic energy, using velocity and a hard, dense penetrator to punch through steel plate by sheer force. Such projectiles became less effective at greater ranges as air resistance slowed them down, and they required hitting the target at close to perpendicular angles to achieve maximum penetration. Shaped charges operated on entirely different physics. The warhead contained a precisely formed cone of metal, typically copper in more sophisticated designs, but sometimes steel or other metals in cruder weapons, backed by a quantity of high explosive. When the explosive detonated, it collapsed the cone from back to front, transforming the metal into a hypervelocity jet of molten and semi-molten particles traveling at speeds up to 8,000 meters per second. This jet didn't punch through armor like a solid projectile. Instead, it eroded its way through the steel in a process that resembled a cutting torch more than a bullet penetration. The jet's penetrating power was largely independent of the velocity at which the warhead itself was traveling when it hit. A Panzerfaust projectile drifted through the air at a leisurely 45 meters per second, yet its shaped charge could defeat armor that would stop a high-velocity anti-tank gun shell. The critical variable in shaped charge effectiveness was standoff distance, the space between the point where the warhead detonated and the face of the armor it was attacking. Every shaped charge design had an optimal standoff distance, typically between 3 and 6 times the diameter of the cone, where the metal jet achieved maximum coherence and penetrating power. Detonate the charge too close to the target, and the jet hadn't fully formed and focused. Detonate it too far away, and the jet began to dissipate and lose coherence, its penetrating power degrading with every additional centimeter of air it had to traverse. This sensitivity to standoff distance had led armor designers to experiment with spaced armor, placing a thin outer plate some distance in front of the main armor, with the theory that a shaped charge would detonate against the outer plate, form its jet at the wrong distance from the main armor, and either fail to penetrate or achieve significantly reduced penetration. The principle was elegant, but the implementation proved devilishly difficult. Make the standoff too short, and you might actually improve the shaped charge's performance by placing the main armor closer to the optimal distance. Make it too long, and you had to extend the outer armor so far from the vehicle that the tank became impossibly wide, unbalanced, and mechanically unreliable. The Germans themselves had experimented extensively with Sherman, thin armor skirts mounted around tank turrets and hull sides, but these were primarily designed to defeat Soviet anti-tank rifles, not shaped charges, and they had to be mounted on brackets that could be detached for maintenance rather than welded permanently, limiting their effectiveness. British and American ordnance officers and military scientists understood these principles by mid-1944, and as reports of improvised armor modifications flooded back from Normandy, several organizations conducted formal tests to determine whether the crew's desperate improvisations actually provided any protection. The results of these tests varied, but the overall conclusion was sobering. In trials conducted by Allied ordnance units in late July and August 1944, captured Panzerfaust warheads and comparable shaped charge munitions were fired at test panels representing various improvised armor schemes. A test firing against armor protected by track links spaced approximately 12 inches from the main plate, about the typical distance achieved when links were hung on welded brackets, showed that the track links detonated the shaped charge prematurely, but that the resulting jet still retained sufficient power to penetrate the main armor in most cases. In some trials, the track links actually appeared to optimize the standoff distance, placing the main armor precisely where the shaped charge jet achieved maximum penetration, resulting in deeper penetration than would have occurred had the shaped charge detonated directly against the armor. The analysts concluded that to reliably defeat a Panzerfaust, spaced armor would need to be positioned at least 75 centimeters, nearly 30 inches, in front of the main armor, and even this might not provide complete protection. Achieving such spacing would require extending brackets that far from the hull, creating a massive projection that would catch on every obstacle, make the tank difficult to maneuver in confined spaces, and add such weight that the already overtaxed engine and transmission might fail completely. The test reports landed on the desks of senior commanders with recommendations that ranged from discouraging to actively prohibiting the practice of adding improvised armor. A technical intelligence bulletin distributed to British formations in August 1944 noted that the addition of track links or other improvised armor in close spacing to the hull provides negligible additional protection against shaped charge attack and may, in certain circumstances, increase the effectiveness of enemy hollow charge weapons. The added weight reduces mobility, increases mechanical failures, and provides no significant tactical advantage. The British Ordnance Staff recommended that crews cease the practice immediately. American ordnance officers reached similar conclusions, and the U.S. First Army issued guidance in September 1944 stating that improvised armor modifications should be undertaken only under direct supervision of ordnance officers after proper testing, and that track links should not be applied without specific authorization. But the crews, facing daily the prospect of a Panzerfaust emerging from a hedgerow or basement window, largely ignored these recommendations. The disconnect between what rear area analysts concluded from controlled tests and what frontline crews experienced in the chaos of combat was absolute and unbridgeable. From the analyst's perspective, the physics were clear. Improper standoff distance did not defeat shaped charges. Added weight degraded vehicle performance, and the modification provided no measurable benefit. From the crew's perspective, the calculus was entirely different. They knew tankers whose Shermans had been hit by Panzerfausts and survived, whether because the warhead hit at a bad angle or the fuse malfunctioned or the jet happened to miss critical components, or because the track links happened to disrupt the warhead in just the right way to reduce penetration. They heard stories, impossible to verify but repeated with conviction, of tanks where a Panzerfaust had hit the track link armor and failed to penetrate, allowing the crew to escape or even continue fighting. Whether these stories reflected the actual protective value of the track links or simply the normal variation in combat outcomes, some hits are always less effective than others for dozens of random reasons, mattered less than the psychological comfort they provided. The modification also served a crucial morale function that the analysts' reports failed to consider. Tank crews in Normandy felt helpless, trapped inside thin-skinned vehicles facing weapons they could neither see before the attack nor effectively protect against with maneuver or tactics. The Panzerfaust attacked the fundamental bargain that armored warfare offered. The crew accepted being enclosed in a vulnerable metal box in exchange for the protection that armor provided. When the armor proved inadequate, when an enemy who might be anywhere could kill you with a single shot from a disposable weapon that cost less to manufacture than a crew member's monthly salary, the psychological contract broke down. Adding track links, even if their actual protective value was minimal or non-existent, restored a sense of agency. The crews were doing something, taking action to improve their odds, exercising some control over their fate rather than simply accepting their role as targets. The welding, the scavenging for links, the careful placement of each section. All this activity channeled the crew's fear and anger into productive work, transforming them from passive victims into active participants in their own survival. Senior commanders, recognizing the morale value even as they understood the limited practical benefit, chose not to enforce the prohibition too strictly. A memo circulated within 21st Army Group headquarters in late August 1944 noted that while technical analysis suggests limited utility for improvised armor modifications, field commanders report that such modifications significantly improve crew morale and confidence. Given the intense stress under which tank crews are operating, prohibition of these modifications might do more harm than allowing them to continue, provided they do not significantly impair vehicle mechanical reliability. The unstated calculus was pragmatic. If the track links didn't actually help much but made the crews feel better, and if that improved morale translated into greater tactical effectiveness, crews willing to press attacks, to hold positions, to take necessary risks, then the modification paid for itself regardless of its actual protective value. The added weight did stress drivetrains, and units reported increased mechanical failures attributable to overloading, but these losses were accepted as part of the price of keeping crews psychologically capable of continuing the fight. The German perspective on Allied improvised armor modifications was, paradoxically, more scientifically rigorous than the Allied approach. The Nachrichtenblatt der Panzertruppen, the official newsletter for German armored forces, published a detailed analysis in its September 1944 edition based on observations of captured Allied tanks and interrogations of prisoners regarding field modifications. The report, prepared by a Waffenamt officer, the German Army's Weapons Development and Procurement Office, noted that Allied tank crews had been observed attaching various improvised armor schemes to their vehicles, including track links arranged in various patterns, logs and timber, concrete, and sandbags. The analysis was methodical and damning. Track links placed at shallow angles does not offer any significant additional protection. When placed at an angle of 80 to 90 degrees, they will even reduce the armor protection compared to that of the armor plate alone. The report explained that track links positioned nearly perpendicular to the hull actually created a more favorable striking angle for armor-piercing projectiles, causing them to impact more directly rather than glancing off, and that the track links provided insufficient spacing to disrupt shaped charge formation effectively. The German analysts calculated the additional weight imposed by these modifications, observing one captured Panther that had been up-armored by its crew with 48 track links weighing nearly 1,500 kilograms in total, and concluded that this weight will increase the strain on the drivetrain, engine, and gearbox without providing compensating protection. The German report also addressed concrete armor, another improvised modification that some Allied crews had attempted. Tests conducted by German ordnance engineers demonstrated that a 75mm anti-tank shell from the Pak-40 could penetrate between 60 and 100 centimeters of concrete at short range, meaning that the typical 20-centimeter thick concrete layer that crews could practically apply offered minimal protection while adding enormous weight, approximately 600 kilograms per square meter. Following a firing trial, the report concluded, the reinforcement of armor by the use of concrete is not found to be advisable. The weight is high and the fragmentation effect is unfavorable, and it has therefore been rejected by the Ordnance Office. The fragmentation effect referred to the dangerous secondary projectiles created when concrete was struck by high explosive shells. Rather than absorbing the blast, the concrete shattered into deadly shrapnel that endangered nearby infantry and could damage the tank's own external equipment. Yet even as German technical analysts documented the ineffectiveness of improvised armor, German tank crews engaged in exactly the same practices, welding track links and concrete to their own Tigers, Panthers, and Panzer IVs. The Nachrichtenblatt report acknowledged this explicitly, noting that the analysis was prompted partly by observations of German crews adding improvised armor in the field without authorization. The German High Command faced the same dilemma as their Allied counterparts. Scientific analysis said the modifications didn't work, but crews insisted on making them anyway, driven by the same psychological need to do something to improve their odds. The Germans were somewhat more successful in enforcing their prohibitions. Welding on improvised Sherman was strictly forbidden due to concerns that the welding process might weaken the factory armor plate, and concrete armor was banned outright after the tests demonstrated its problems. But the Wehrmacht compromised by authorizing properly engineered bolt-on track link arrangements and factory-produced Sherman, giving crews an officially sanctioned version of the modifications they were making anyway. The reality of combat in Northwest Europe from August 1944 through the end of the war was that shaped charge weapons, Panzerfausts, Panzerschrecks, and their allied equivalents like the American bazooka and British PIAT, accounted for an enormous percentage of armored vehicle losses. A British study of tank casualties during operations in March through May 1945 found that shaped charge weapons caused nearly as many penetrations as conventional armor-piercing guns, despite being far shorter ranged and less accurate. The study noted that the majority of tank casualties were the result of fire from 75mm guns, but hollow charge weapons like the Panzerfaust were the second most common cause of penetrations and fires. Perhaps most significantly, the study found that the majority of casualties, both direct and indirect, were the result of penetrations of the armor by AP hits, and that fires were mainly the result of ammunition burning or exploding. This last point was crucial. The real killer wasn't the shaped charge jet itself, but the secondary effects when the jet penetrated into the crew compartment and ignited ammunition or fuel. A penetration that missed the ammunition racks and fuel tanks might wound or kill some crew members but leave the tank reparable. A penetration that ignited the ammunition turned the entire vehicle into a death trap within seconds. The British analysts concluded that improvised side armor, including track links, was better utilized directly on the front of the tank and also in protecting the crew from the ammunition inside. This reflected a sophisticated understanding of the actual threat pattern. Most German anti-tank fire struck tanks from the front during combat, not the sides or rear, and the greatest danger came not from the initial penetration but from the ammunition fires that followed. Better designed ammunition storage with armored bins and blowout panels, features that later American tanks would incorporate, would save more lives than any amount of improvised external armor. But such redesigns required factory modifications, new production runs, and time that the crews fighting in Normandy in the summer of 1944 simply didn't have. The largest British armored operation of the Normandy campaign, Operation Goodwood, launched on July 18, 1944, provided a grim demonstration of the Sherman's vulnerability even with improvised modifications. 3 full armored divisions, the 7th, 11th, and Guards Armored Divisions, equipped with more than 1,000 tanks including several hundred Shermans, many of them sporting improvised track-link armor, attacked German positions southeast of Caen following the massive aerial bombardment. The assault made initial progress, advancing up to 7 miles in some sectors, but the German anti-tank defense, a carefully prepared network of 88mm anti-aircraft guns used in the ground role, dug-in Panthers, and infantry positions equipped with Panzerfausts, brought the advance to a bloody halt. British tank losses during the 3-day operation remain debated, with figures ranging from 218 to 469 tanks knocked out, though many were recovered and repaired. Even the conservative estimate of 218 tanks lost represented nearly 20% of the attacking force, while the higher figures suggested losses approaching 40%. Infantry casualties in the supporting operations exceeded those of the tankers, with 3 infantry divisions suffering more than 2,700 casualties compared to 1,149 in the armored divisions. The operation succeeded in its strategic objective, pinning German armor in the British sector so that American forces could break out to the west, but the tactical cost demonstrated that neither the Sherman's basic armor nor the improvised modifications could provide adequate protection against the concentrated anti-tank defense the Germans could bring to bear. The crews who survived Goodwood and the subsequent operations through the summer and fall of 1944 developed a sophisticated understanding of what actually provided protection in armored combat. Tactical skill mattered more than armor thickness. Using terrain for cover, presenting the smallest possible target, maintaining situational awareness to avoid ambushes, coordinating with infantry to clear buildings and hedgerows before tanks advanced through them. The Firefly, a Sherman mounting the British 17-pounder anti-tank gun, capable of engaging Panthers and Tigers at range, was worth its weight in gold because it allowed British tank units to engage German heavy armor from distances where the German tanks couldn't easily return fire. Close coordination between tanks and infantry prevented Panzerfaust teams from getting into position for killing shots. Artillery and air support suppressed German anti-tank positions before tank attacks had to go in. All of these tactical and operational measures demonstrably reduced casualties more effectively than welding track links to hulls. Yet the track links remained, festooning British and American Shermans throughout the Northwest Europe campaign. Photographs from the liberation of Brussels in September 1944 show British tanks draped with track links, sandbags, logs, and spare road wheels. Images from the fighting in Holland during Operation Market Garden, the desperate battles in the Reichswald Forest, and the final push across the Rhine into Germany all show tanks carrying improvised armor that technical analysts had concluded was ineffective months earlier. In some cases, the modifications evolved, crews learned to space track links in specific patterns, to angle them rather than mounting them flat, to combine them with sandbags or timber to achieve better standoff distances. In other cases, crews abandoned the track links as too heavy and unreliable, preferring lighter modifications or accepting their vehicle's base armor as adequate. The practice became part of the visual culture of the Allied tank forces in Northwest Europe, as characteristic as the white star markings on American vehicles or the ram's head insignia of British armored divisions. The post-war assessment of improvised armor modifications has been mixed, reflecting the complexity of evaluating a practice that provided limited technical benefit but significant psychological value. The U.S. Army study of field expedient modifications, completed in 2006 by a military historian reviewing World War II records, concluded that field expedient modifications did not provide significant improvements to the levels of protection to their vehicles in terms of improved performance of the vehicle's basic armor package against traditional anti-armor weapons. The study noted that modifications were most effective against small arms fire and fragments, threats that rarely penetrated tank armor anyway, and did not perform well against high-velocity guns and shaped charges, which were the actual threats that killed crews. This cold assessment, however, fails to capture the human dimension of the practice. The same study acknowledged that commanders like Major General I.D. White of the 2nd Armored Division felt that American tanks were inadequately protected and that crews were justified in seeking any measure that might improve their odds. The psychological dimension of the track link modification extended beyond individual crew morale to the broader challenge of maintaining combat effectiveness in tank units facing extraordinary casualty rates. British armored regiments in Normandy typically entered combat with approximately 50 tanks. Within days or weeks of heavy fighting, they might have lost half their vehicles, with many having to be replaced multiple times as replacement tanks were knocked out in turn. The human cost was even more severe. Tank crews who survived one knocked-out vehicle were often reassigned to another tank, only to be knocked out again, sometimes multiple times. Ken Tout, whose memoir, Tank, became recognized as perhaps the most authentic account of what it was like to crew a Sherman in Northwest Europe, served from D-Day through to the final battles in Germany, and saw his unit's personnel turned over almost completely several times. In such an environment, anything that gave crews the confidence to mount their tanks and drive into combat one more time had value regardless of its technical effectiveness. The German Panzerfaust itself evolved throughout the war, with improved models appearing at regular intervals. The Panzerfaust 30, with its 30-meter effective range and 140mm penetration, was supplemented by the Panzerfaust 60 with 60-meter range and 200mm penetration, then the Panzerfaust 100 with its 100-meter range and even greater penetration. Late war models approached the sophistication of modern anti-tank weapons, with improved sights, better propellants, and more refined shaped charge designs. Against these evolving weapons, improvised armor modifications became progressively less relevant. A weapon that could defeat 200 millimeters of armor would not be significantly inconvenienced by track links adding a few tens of millimeters of equivalent protection. The Allies' ultimate solution to the tank protection problem came not from improvised modifications but from the introduction of new tank designs. The British Comet with its improved armor and armament, the American M26 Pershing heavy tank with its 90mm gun and thicker armor, though these arrived too late to see significant combat in Europe. The broader pattern of field expedient modifications in World War II reflected the enormous gap between what military planners believed troops would need and what combat actually demanded. The Cullen hedgerow cutter, which allowed tanks to punch through Norman hedgerows without exposing their vulnerable undersides, was invented by a sergeant and initially dismissed by higher headquarters before being validated by field testing and rushed into mass production. The Rhino tanks mounting these cutters proved invaluable during the breakout from Normandy, demonstrating that frontline soldiers often had better insights into tactical problems than rear area planners. Tank-mounted telephones allowing infantry to communicate with tank crews, improvised stowage systems, field-applied camouflage schemes, additional machine gun mounts. All these modifications emerged from the crew's direct experience of combat and were often implemented before official approval was granted or technical testing validated their effectiveness. The track-link armor modification fit into this pattern as an example of troops taking initiative to solve a perceived problem, even if the solution was more psychological than physical. The final chapter of the track-link story belongs to the post-war period, when the lessons of World War II shaped the development of the next generation of armored vehicles. Soviet designers, who had observed their own crews applying improvised armor throughout the war and who had the most extensive experience combating German-shaped charge weapons, developed spaced armor schemes and explosive reactive armor that provided genuine protection against shaped charges. The Soviet T-55 and T-62 tanks, developed in the 1950s and 1960s, incorporated lessons learned from the primitive improvised armor of World War II, translating the concept of spaced armor into properly engineered systems with optimal standoff distances and appropriate materials. Western designers pursued different approaches, developing composite armor incorporating ceramics and other materials that disrupted shaped charge jets through entirely different mechanisms. The modern main battle tanks of the late 20th and early 21st centuries, Abrams, Challenger, Leopard bear no visible trace of the improvised track-link armor of 1944, yet they embody lessons learned from that desperate period when crews sought any measure, however crude, to improve their chances of survival. The stupid trick of welding track links to Sherman tanks was ultimately neither stupid nor much of a trick. It was a reasonable response to an impossible situation, a measure that provided marginal and unreliable physical protection but significant psychological benefit, and most importantly, a demonstration of the initiative and determination that characterized Allied tank crews in Northwest Europe. The technical analysts were correct that the modification didn't meaningfully improve armor protection and might sometimes make penetration more likely. But they were wrong to think that this made the modification worthless. In the terror and chaos of armored combat in 1944 and 1945, where death might come from any direction at any moment and where the Sherman's inadequate armor was a known and accepted fact, the track links represented something more important than measurable protection. They represented the crew's refusal to be passive victims, their determination to fight back against overwhelming odds with whatever tools came to hand, their assertion that they were not simply cannon fodder to be expended in the advance across Europe. When British and Canadian troops finally linked up with American forces at Falaise in late August 1944, completing the encirclement of German forces in Normandy, the Shermans that rolled through the devastated pocket bore the marks of 2 months of brutal combat. Many were replacement vehicles, the original tanks that had landed on D-Day long since knocked out and replaced. Most sported hastily applied track-link armor, the links often hanging loose after being damaged by near misses or simply shaken free by the constant vibration of movement across broken terrain. The crews, those who had survived the battles at Caen, Goodwood, Totelise, and Tractable, could compare notes on which modifications had seemed to help and which had proven useless, though any such discussion was inevitably colored by survivorship bias and the impossibility of knowing what would have happened without the modifications. What they knew with certainty was that they had done everything possible to improve their odds, that they had not gone passively to their fates, and that the track links festooning their vehicles symbolized their refusal to accept the Sherman's limitations as a death sentence. The advance continued into Belgium and Holland, then across the Rhine and into Germany itself, and throughout this final campaign the track links remained a common sight on Allied tanks. New crews arriving as replacements learned the practice from veterans and applied it to their own vehicles, perpetuating a modification that technical analysis had discredited, but that operational experience had validated as worthwhile for its morale effects if nothing else. When the war finally ended in May 1945, and the surviving tank crews began the process of standing down their vehicles and preparing for redeployment or demobilization, the track links that had accompanied them across half of Europe were cut away and discarded, reduced again to mere spare parts rather than talismans of survival. But the photographs remained, and the memories, and the historical record of a modification that encapsulated both the Sherman's inadequacies and the resourcefulness of the men who fought in them. The legend of the track-link armor, particularly the notion that it made Panzerfausts bounce off, emerged in the post-war years as veterans told their stories and historians attempted to make sense of the improvisations and expedients that characterized the Allied campaign in Northwest Europe. Like many legends, this one contained a kernel of truth wrapped in layers of exaggeration and misunderstanding. Yes, some Shermans with track-link armor survived Panzerfaust attacks that might have destroyed them otherwise, though whether the track links made the difference or whether the attacks simply missed vital areas cannot be determined. Yes, crews believed the modification helped, and this belief supported morale and combat effectiveness, which was valuable even if the physical protection was minimal. And yes, the modification represented genuine initiative and problem-solving by frontline troops facing weapons their vehicles were not designed to counter. But the legend that track links reliably defeated Panzerfausts, that this stupid trick provided a technological edge against German-shaped charge weapons, has no basis in the historical record or the physics of armor penetration. The track links were a gesture, sometimes a useful one, but never the solution to the fundamental problem of the Sherman's inadequate armor protection. What ultimately protected Allied tank crews in Northwest Europe was not improvised modifications but overwhelming numerical superiority, superior logistics that kept tanks operational and replaced losses faster than the Germans could inflict them, tactical innovations that reduced exposure to German anti-tank weapons, and most fundamentally, the gradual attrition of German combat power to the point where effective resistance became impossible. By early 1945, German infantry rarely had Panzerfausts in sufficient quantity to threaten every Allied tank. Anti-tank gun positions were not sufficiently dense to cover every avenue of approach, and Panther and Tiger tanks appeared only in small numbers as German production collapsed. The last battles, the Reichswald, the Rhine crossings, the final advance through central Germany, saw far fewer tank casualties than the Normandy battles, not because Allied tanks had improved but because German defensive capabilities had degraded catastrophically. In this final phase of the war, the track-link armor remained as much because removing it required effort as because crews believed in its effectiveness. The historical memory of World War II's armored warfare has focused overwhelmingly on the glamorous aspects, the tank versus tank duels, the charges across open terrain, the dramatic technological contest between armor and anti-tank weapons. But the reality experienced by tank crews was more mundane and more terrifying. Hours of maintenance, stretches of boredom punctuated by moments of extreme violence, the constant awareness that death might come at any second from weapons they could neither see nor effectively counter. In this reality, the track links welded to Sherman hulls served their purpose not by providing measurable protection but by giving crews something to do, some sense of control, some visible symbol that they were taking action to protect themselves rather than simply accepting their fate. This was not a technological solution but a psychological one, and in the brutal environment of armored combat in 1944 to 1945, psychological solutions were sometimes as important as technical ones. The British tankers who festooned their Shermans with track links knew, at some level, that the modification was not a silver bullet, that it would not transform their vulnerable medium tanks into impregnable fortresses. They knew the Panzerfaust could still kill them, that the 88mm gun could still penetrate their armor from a kilometer away, that a direct hit from a Panther could still brew them up in seconds. But they also knew that combat demanded action, that passivity meant death, and that even a marginal improvement in their odds justified the effort. The track links were their answer to an unanswerable problem, their solution to the Sherman's inadequacies, their defiance in the face of German anti-tank weapons that rendered armor thickness almost meaningless. It was a stupid trick, born of desperation and maintained through faith rather than evidence. But it was also a very human response to the inhumanity of industrialized warfare, and in that context it deserves to be remembered not for what it actually accomplished but for what it represented. The determination of ordinary soldiers to fight back against their circumstances with whatever tools came to hand, and to assert their agency even in situations where agency seemed impossible.